In this video, we will demonstrate the mesh-wise data collection and network monitoring application responsible for collecting and displaying sensory measurements, network statistics, and status information on both the IoT wireless sensor network and the mesh network infrastructure used in the mesh-wise final trial. As an introduction, let's have a look at the high-level architecture of the trial testbed. It consists of three distinct parts, namely the backbone network that includes three mesh nodes communicating over Wi-Fi, the IoT network comprising of two IoT gateways, and the monitoring server acting as the system backend. In this scenario, the IoT gateways, named Demo Gateway 1 and Demo Gateway 2, are connected over Ethernet to mesh node 2, and data collected from them, and thus from the sensors registered to them, is forwarded to the monitoring server that is connected to mesh node 1, also over Ethernet. The web-based monitoring application that is fully implemented using the Node.js framework runs in the monitoring server. In this block diagram, the components that comprise the monitoring server are displayed. Essentially, the data collection functions are performed by a data acquisition engine that receives sensory measurements exposed as COAP resources from the sensor devices and forwarded over HTTP by the IoT gateways through the mesh network. These measurements, along with network and operating system status information that is periodically pulled by appropriate observers, both from the sensor and mesh network, are stored in a MongoDB document-oriented database. Stored data can be easily retrieved from the database and exposed to the internet through a web server lying in the monitoring backend. Requested data are visualized in the form of charts and tables and displayed in appropriate web pages. Now let's have a look at the web interface of the mesh-wise monitoring application. In this page, an overview of the IoT gateways is presented, namely name, IP, online status, number of online out of total IoT sensors devices of current gateway, and timestamp of last online appearance. By clicking on the name of a gateway, a similar overview for the sensor devices communicating with this gateway is shown. Information displayed includes sensor ID, IP address, model type that corresponds to different sensor combinations, online status, and time from last activity. Further, measurements received from each sensor device that describe weather conditions, air quality, etc., as well as power consumption, link quality, and network statistics are visualized in charts and tables. Next page displays an overview of the mesh network, including name, IP address, online status, serial number, system uptime, and timestamp of last online appearance. Followingly, timely and short-term historical operating system information like CPU load, memory usage, and network traffic per interface is visualized for each node. Now, we present a scenario of efficient IoT network traffic handling in the case of partial failure of the mesh network as captured by the monitoring application. Initially, all mesh nodes are online and all traffic is routed from node 2 to node 1 through node 3, since this route is the less costly. Both gateways are online. Next, we artificially create a mesh node failure by powering off node 3. During the first seconds of the failure, the IoT gateways are unable to forward measurements and status information to the monitoring server, since no route exists between them. As a result, their status marked as offline. However, as the mesh network self-healing mechanisms respond to the failure, a new direct route between node 2 and node 1 is formed. Finally, after almost 30 seconds, communication between IoT gateways and the monitoring server is restored, gateway status returns to online, and sensor measurements collection and storing is again possible.